Hey everybody, and welcome to Numerical Analysis Lecture 8. Remember in our previous lecture, we were talking about how we can approximate the definite integral of f of x, where f of x is some continuous function. And we sort of recapped the history of where the definite integral came from. We formed a Riemann sum where each term of the Riemann sum is the area of a rectangle bounded on top by the graph of f of x and bounded on the bottom by the x-axis. And we did that because we realized that if f of x is non-negative, then the definite integral of f of x from x equal a to x equal b is the area between the graph of f of x and the x-axis from x equal a to x equal b. And we said, well, hey, why don't we just split the interval from a to b into n subintervals of equal length, and each of these subintervals is going to have a width of delta x. And above every single subinterval, we're going to construct a rectangle, the base of which rests on the x-axis, and the top of which passes through the point x of I, f of x of I. So, for example, in the ith subinterval, where I is typical of the ith subinterval is typical of all subintervals from the first subinterval to the nth subinterval. Over the ith subinterval, we have a rectangle of width delta x. We pick a point in the ith subinterval. We call it x of I. The base of the ith subinterval rests on the x-axis, and the top of the ith subinterval goes through the point x of I, f of x of I. And we do this for all rectangles. We do this rather for all subintervals from the first to the nth subinterval. And the area of the ith subinterval is the width, delta x, times the height. And the height of this rectangle is the y-coordinate at this point, which is f of x of I, minus the y-coordinate at this point, which is 0. So the height of this rectangle is just f of x of I. So the ith term of the sum represents the area of the ith rectangle. F of x of I is the height, delta x is the width. And we said, there is a problem with this. The tops of the rectangles don't conform precisely to the contour of the graph. So sometimes the top of the rectangle pokes out above the graph of f of x and includes area that shouldn't be included in our approximation. Other times, the top of the rectangle falls below the graph of f of x and excludes area that should be included in our approximation. So we have a problem with accuracy because the tops of the rectangles don't conform precisely to the contour of the graph. And we said, no problem, we'll just make the rectangles thinner. And if the rectangles are thinner, the tops of the rectangles will conform more closely to the contour of the graph. And that's true. The problem is we can't let delta x get smaller and smaller and smaller and continue to get increased accuracy. There's an optimal value of delta x depending on what the precision of our variables and precision of our functions is. And that optimal value may be 0.01, it may be 0.001. But here's what's going to happen if we make delta x smaller than that optimal value. We'll be gaining accuracy because we'll make the rectangles thinner, but then we'll be losing accuracy because of the round-off error that's involved in doing so many computations. See, if we make delta x smaller, that means that we have to have more rectangles, and we do more computations computing the area of each rectangle. So we're not going to get the perfect approximation by letting delta x get smaller and smaller and smaller. The thing to do is just to let delta x equal the optimum value, and maybe that's 0.01 or maybe that's 0.001. Whatever it is, we let delta x equal the optimal value, and that's the best approximation for the integral that we're going to get using this technique. So I guess that begs the question, can we change what we're doing in some other significant way other than to let delta x get smaller and smaller, or other than let delta x be the optimum value? And the answer is yes. We're still going to let delta x equal the optimum value, but we're going to pull a few other strings to make our computation or our approximation better as well. And here's the first thing that we can do. We start off with the same scenario. We have the interval from A to B, and we divide that interval into n subintervals of equal length, and we call that the length of that subinterval delta x. And we let A be x of 0. And the endpoint of each interval after that be x of 1, x of 2, and so forth. So this is going to be x of 1. This will be x of 2. And note, x of 1 is the right endpoint of the first interval. X of 2 is the right endpoint of the second interval. X of n is the right endpoint of the nth subinterval. So if this is the ith subinterval right here, then the right endpoint will be x of I. The left endpoint will be x of I minus 1. And is that visible? I guess that's visible on our video. And we like the idea of constructing rectangles, but somewhere along the line, somebody said, you know, why does it have to be a rectangle? Why can't we do this instead? From the x-axis, we'll extend the line up until it hits the graph for each x of I. Whoops. And we'll look at that, and you're saying, well, we're certainly not going to get rectangles if we draw the lines like this. And you're right, but we'll get something that's almost a rectangle, but it works a bit better. Instead of a rectangle, we'll have a trapezoid. We'll take the points of intersection of the vertical lines on either side of a subinterval and connect them with a line segment. And now, even for fairly large delta x, the tops of these trapezoids conforms a little bit more closely to the contour of the graph. Now the only thing we have to do is compute the areas of each of these trapezoids, add up the areas of the trapezoids, and we've got ourselves an approximation of the definite integral. First of all, I guess we better agree on just exactly what a trapezoid is. A trapezoid is a four-sided region that has two sides that are parallel. So here's a trapezoid. It has four sides, 1, 2, 3, 4. And two opposite sides are parallel. It's a trapezoid. And how do we compute the area of a trapezoid? It's going to be the average of the lengths of the parallel sides times the height, or times the distance between the two parallel sides. And we'll say height or distance between the parallel sides. In our drawing of the trapezoid here, h is the height of the trapezoid. It's also the distance between the two parallel sides. So we're going to apply this to the trapezoids that we're using to fill up the region between the x-axis and the graph of f of x. To figure out how we're going to compute the areas of all of these trapezoids, let's just focus our attention on the ith trapezoid, the trapezoid that's over the ith subinterval. Whatever we figure out about this ith trapezoid is going to be typical for all of the trapezoids. For n equal 1, the first trapezoid, for n equal 2, the second trapezoid, so forth and so on. Whatever we figure out about the ith trapezoid will provide a model for how we compute the areas of all of the other trapezoids. So let's see. The upper left endpoint of the ith trapezoid has coordinates x of I minus 1 and f of x of I minus 1. The y coordinate, f of x of I minus 1. Now, go down to where the trapezoid rests on the x-axis. What's the y coordinate of this point? The point's on the x-axis, so y equals 0, right? And the length of this side goes from y equals 0 to y equal f of x of I minus 1. The length of this side is the difference of the greater y coordinate, f of x of I minus 1, minus the lesser y coordinate, which is 0. So the length of this side is f of x of I minus 1 minus 0, or f of x of I minus 1. Now let's look at the right side of the trapezoid. The right side of the ith trapezoid. Again, the trapezoid sits on the x-axis, so the y-coordinate of this point is 0. The y-coordinate of this point, where the trapezoid intersects the graph of f of x, is f of x of I. The length of this side is the greater y-coordinate, f of x of I, minus the lesser y-coordinate, 0. The length of this side is f of x of I minus 0, or just plain f of x of I. So we have the lengths of the parallel sides. Now, what about the distance between them? Oh my goodness, that's the easiest part to figure out. The distance between these two parallel sides is just the width of the subinterval, which is delta x. Son of a gun. That is going to be very easy to figure out. See, the area is going to be the average of the lengths of the parallel sides times the space between them, which is delta x. So the average of these lengths, f of x of I minus 1 plus f of x of I minus f of x of I over 2 times delta x. So this is the area of the ith trapezoid. So here's how we approximate the definite integral of f of x from x equal a to x equal b using the trapezoidal method. We add up the areas of the trapezoids. Capital A sub I is the area of the ith trapezoid. And we let I go from 1 to n. This is explicitly how the area of the ith trapezoid is computed. And we'd love to be able to let delta x get smaller and smaller and smaller, but we can't. Sooner or later, delta x is going to assume that optimal value. And if we let delta x get smaller than that, any accuracy that we gain by letting delta x get smaller will be outweighed by the round-off error that occurs because we're doing so many computations. If we let delta x get smaller, we're going to have more trapezoids. That means more computations. So there is a break-even point, an optimal value of delta x, depending on the precision of our variables and precision of our functions and so forth. It may be 0.01, 0.001, something like that. So what we'll do is we'll just evaluate the Riemann sum at the optimal value of delta x and let it go at that. But there are some things that we can do to cut down on the number of operations. Look at what we're doing here. For each term of the sum, we're computing f of x sub I minus 1, and we're computing f of x sub I. We're adding those two together, and we're dividing by 2, and then we're multiplying by delta x. We can cut the number of operations in half right there by doing this. Just compute these things. Compute this whole sum, and then afterwards, just multiply by delta x over 2. So if we have 100 of these things to add up, that means that we're going to be computing this sum 100 times. We're going to be dividing that sum by 2 100 times. Then we're going to be taking that whole thing and multiplying it by delta x 100 times. This way, we're computing all of these sums and adding them up, and then we're multiplying by delta x once and dividing by 2 once. We cut down on the number of operations. Now, that's how we do it. How do we define f of x sub I? How do we define x sub I minus 1 and x sub I? Let's just make sure that we have that straight. So how do we compute our x sub i's? X sub 0 equals a. X sub 1, let's see, we start at a and we go a distance of delta x. So this is a plus delta x. What's x sub 2? We start at x sub 1, which is a plus delta x, and we go a distance of delta x. So this is a plus 2 delta x. And similarly, x sub 3 is a plus 3 delta x. And x sub I in general is going to be a plus I delta x. And this guy, x sub n, which is b, is going to be a plus n delta x. Not quite. For I equals 0, 1, 2, n, x sub I equals a plus I delta x. So this is how we get our f of x sub I minus 1 and our f of x sub I. That is the trapezoidal rule. Let me just check and make sure I've told you everything that you need to know. I have told you everything that I need to tell you for right now. Short lecture for today. The next lecture will be a little bit longer. Today we talked about how we can improve on our approximation of a definite integral. Next lecture we'll talk about a way that we can improve even more. And I think you'll find this particular method kind of amazing. It involves a mathematical fact that At one time in my life, I would have bet, no, I don't see how that could possibly be true. It's got to be false. But the next improvement that we're going to make on approximating definite integrals involves a mathematical fact that we probably don't know. And it's somewhat of an amazing mathematical fact. It's going to prove very handy for improving our approximations of definite integrals. And I think you're going to like it.